this lesson, we will wrap up our discussion on decision trees. We will discuss decision tree size, overfitting, pruning, and visualization. Let's consider this decision tree. This decision tree correctly classifies every instance. Each leaf is true or false. However, the tree is somewhat deep. So a key question is, can we achieve the same accuracy but with a smaller tree? Consider this smaller decision tree. The leaves represent final decisions, but the structure is simpler. The first split remained unchanged, but the subsequent splits have been adjusted, making this tree more concise. So the argument here, when we presented between two models or hypotheses, the simpler choice is more likely the one that can generalize better. Overfitting can happen in decision trees, which means the model memorizes the training data instead of learning the general patterns. In this visualization, we have a two-class problem, spam, no spam. As you can see, the black line, which is simple boundary, was able to separate most cases, but it made a few mistakes. On the other hand, the green line is more complex. It went above and beyond in this wiggly fashion and managed to classify every example correctly. But this may not generalize in the real world because most probably these are outliers or noise or very special cases. So you don't want to specialize your classifiers to learn those extreme cases. Why overfitting is a problem? We really don't want our model to pick up those random variations, and we need to find the true predictive signals inside the training data. In the following visualizations, we compare different decision trees based on size. So in the first case, this is a root-only tree, sometimes called a decision stump, which most probably inaccurate, but it remains simple and interpretable. And also I want to note that ensembles of such simple trees called boosting can be very powerful. The second visualization is the partially expanded decision tree. We have a root and a few expanded nodes. This structure strikes a balance between complexity and accuracy. Probably it's going to make some mistakes, but captures meaningful patterns most of the time. The third tree is the fully expanded, which is going to capture all training points correctly. But since it has too many nodes, it's going to be hard to interpret and more likely overfit by learning noise rather than true patterns. To overcome overfitting, we can apply pruning techniques. Pre-pruning, also known as early stop, stops the tree from growing too deep by halting splits that do not significantly reduce the error. In other words, instead of constructing a full tree, then pruning it afterwards, pre-pruning stops early when additional splits provide minimal improvements. Unlike pre-pruning, which stops tree growth early, post-pruning will allow the tree to fully grow, and then it trims it back by removing less meaningful splits. In other words, it's going to prune the tree until cross-validation error is minimized, which is going to ensure that we keep only the most valuable decisions. Decision trees remain widely used due to their scalability. They can handle large data sets efficiently. Efficiency can be parallelized for faster computation. Interpretability, easy integration can be adapted inside database management systems, and they have competitive accuracy and perform well, especially in ensembles. Here's a tiny intro to ensembles. So instead of relying on a single tree, ensembles combine hundreds of trees, each giving a prediction. Then a final decision is made through voting or weighted averaging. Somewhere between the 90s and early 2000s, ensemble methods like Random Forest and XGBoost dominated the predictive modeling space. Finally, standard packages like Scikit-learn can visualize decision trees effectively. In summary, we wrapped up our discussion on decision trees. We discussed decision tree size, overfitting, tree pruning, and visualization.